we go. All right, so, all right. Let me share this one more time just in case. So, obviously, we just took our test the other day. So we're going to cover 5-4 and 5-5. This is probably the last piece we're going to be able to cover. We're technically supposed to cover 6-6, but I don't think we'll have the time. This is the first semester that I've not been able to get there. But it's not the end of the world if we don't get to it, so it's not terrible. Anyway, so 5-4 and 5-5 we'll talk about today, and most likely on Monday. We might have to finish a little bit after the Monday after Thanksgiving, but hopefully not. So let's get started so we can get through as much as possible. So a while back when we were talking about derivatives still, we talked about the units and then we interpreted the derivatives. So now we essentially have to do the same thing, but for the integrals. So remember that an integral is a limit of a sum. So we have this really scary, limit definition. But remember that this is just a Riemann sum, and so these are just areas of rectangles. Dun, dun, dun. So if you think about this as actually being a rectangle, we had some width t and some height f of t. So technically we were adding up a bunch of things that were some f of t times t. So since this, goodness, I hate when it does that. So since that delta t in the back can be essentially thought of as a small difference in t, the terms that we're actually adding up in that sum can be thought of as a product of the form f of t times a small difference in t, which essentially gets us that the units of an integral are going to be the units of f of x times the units of x. So if you ever want to find the units of an integral, find the units of the y values and multiply it by the units of the x values. One other note I want to make really quick about units is that the units of a and b are, oh, sorry. I put my chat away. Ooh, I forgot about that, Kayla. Let me write this down, then we'll talk about that in a second. So the units of a and b are equivalent to the units of x. So whatever the units of x are the same as the units of a and b. Kayla asked about homework. You're going to have one last homework assignment. So there's going to be one last homework assignment going up on Monday. I'll probably let it run a little longer than usual. It probably won't be as long as usual either. Maybe I shouldn't say that because some of them were pretty short. But since we have Thanksgiving plopped in the middle, I might extend it, past Monday, even though classes end on that Tuesday after Thanksgiving. Anyway, but there will be one last one, and then you'll be done homework. So you can always go back into Wiley and do homework from the past. The way I have it set up, you don't get full credit for it because it's late now, but you can do them and get points on it, and any points are better than no points. We do have class next Monday. We have class on the 23rd and the 30th, and those are our last two classes. So we do have Monday classes. So yeah. Sorry, my phone is. All right, so where was I? Units of the integral. So we have units of f of x times the units of x. So say, for example, we were looking at a velocity function that was in meters per second, and time was therefore in seconds. Then the units of the integral, if we were taking an integral of that velocity, then that would just be meters per second times seconds. So the integral value would just be in meters. So we're going to do a couple of those. Oh, I misread your thing, Kayla. Don't we have class next Monday? And yes, we do. We have 2 more classes, both on Mondays. I misread that. Anyway, so let C of t represent the cost per day to heat your home in dollars per day, where t is time measured in days and t equals 0 would correspond to January 1st, 2018. And we want to interpret the integral from 0 to 90 of ct dt. So first let's talk about just the units for a second. So the units here, so it would be the units of C of t. So C of t is in cost per day. So we have cost per day. Now technically cost, I did a bad there. Cost is in dollars, so it should be dollars per day. Because if you just say cost per day, what's the cost in? Is it dollars? Is it, you know, pounds? Is it what? Francs? What is the other currency? I don't remember. Anyway, dollars per day. And then we have to multiply that by the units of t, which are just days. So essentially those day units cancel each other out, and this is going to just represent something in dollars. So essentially that integral value is just a dollar amount. So what kind of dollar amount, what does it mean in terms of this context? Well, if those 0 and that 90, so the 0 and the 90, that's a very bad 0. The 0 and the 90 have the same units as x, sorry, t in this case, which would be days. So essentially we're saying from day 0 to day 90, and we're going to have an amount in dollars. Now remember what C of t actually is. It's the cost to heat your home. So essentially this is going to be the cost to heat your house for those first 90 days. So this would be some interpretation. Would be the cost to heat your house for the first 90 days. If you wanted to say of 2018, that'd be probably a little better, but not really necessary. If you wanted, so there's a couple different ways you could phrase this. This one is kind of the better English, if you will. Another way, and this is the one that's kind of like always works, but sometimes sounds really bad, is you can always write it as a change in, so change in something, and I'll write the something down in a second, between day 0, whoops, and day 90. And the change here would be the change in the cost to heat your house. So the change in the cost to heat your home. Oh no, I ran out of space. Pretend that home got squeezed in there. So you can always phrase these. That's kind of like the cookie cutter way to do it. It's a change in the y value units between the two bounds. So I could have said change in the cost to heat your home. Maybe I should say in dollars to say the units between day 0 and day 90, which would get the point across here and would answer the question. But a better way to write it in general English would be the cost to heat your house for the first 90 days. But you can always kind of use that cookie cutter way, because y'all know I don't care about whether or not it sounds good in English. Anyway, so let's do a couple more of those to get that kind of settled underneath our belt here. Are there questions on that one before I go to the next two? Okay. So say I want to interpret this integral from 1 to 3 of v of t dt, where v of t is in meters per second and t is in seconds. This is essentially a velocity. So let me just list my units first. So since we would need the units of v of t, that would be meters per second, times the units of t, which is just seconds. So this integral is just going to be in meters. Sorry, I'm just thinking about something that I phrased badly in the last one. So I'm trying to think of a way to phrase it to make it better. And the last one, when I was reading it in its cookie cutter way, I said Y value units. That was incorrect. I should have said something like the integral units. So here, this would be a change in meters or a change in distance. So you don't necessarily have to say the actual full units as long as it gets the point of the units across. So in the last one, technically the integral units were dollars, but it was a dollar amount to heat your house. And here it's meters, but meters is a distance. So we could say change in distance. And I'm actually going to use that cookie cutter way for this interpretation here. So I'm going to say change in distance. And let me go ahead and put in meters to be super good about stating my units. Between t equals 1 and t equals 3. Again, that one really doesn't sound like decent English. It's not like a great contextual sentence, but it gets the point across. And really, without much more context here, we don't know, is it a car? Is it something else? There's no way to really phrase it as just a general velocity in a much nicer way. So this would kind of be the best way to do it. Change in distance between t equals 1 and t equals 3. Now, another way you could phrase it is, well, no, I'm not going to say that. This would be the best way to phrase it. No, I should say that. Anyway, sorry, I'm a little scatterbrained today. So would we ever need to say t equals 1 seconds? Should probably tack it on to the end. That would probably be good formatting. Would I necessarily be a stickler for it? Probably not. But we should probably include the units there if we're trying to be good about it. So let's go ahead and say, let's just always include it at the end, the units of the A and the B at the end, and I'll start actually being good about that. So let's go ahead and put those down. Oh, wait. Was that not your question? You mean like not having it as t equals 1 and t equals 3 and phrasing it as like 1 second and 3 seconds? Oh, maybe no. Maybe I did get it. I don't know. So again, there's a couple different ways you could phrase this. You could say change in distance in meters between the first second and the third second. You could say something like that. It's more wordy, less t equals. You could say something like change in distance in the 2 seconds between t equals 1 and t equals 3. You could phrase it a bunch of different ways as long as it gets the point across that this is a change in something between those two bound values. Ooh, sorry, I freaked out a little bit. For this next one, we're going from 2005 to 2011 of f of t dt, where f of t is a rate of population growth in millions of people per year, and t is in time in years. So let's talk about units first. So we need the units of f of t, which is in billions of people per year. So billions of people per year. Multiplied by the units of t, which is just years. Those years essentially cancel each other out. And so the units of this integral are just going to be in billions of people. I'm going to use the cookie cutter way again. So a change in, now technically we're talking about a population here. So we're talking about a change in population in billions of people. So this would be a change in population. Well, that looks weird. Billions of people. (2005) and 11. I didn't put t equals 2005 and t equals 2011 here, just because they're years, the units and the context kind of come across a bit nicer. So notice I didn't say 2005 and 2011 years, and again, that's technically because the context of a year is it comes across in that number. If the unit doesn't come across in the context like that, like in the first one, it was t equals 1 and t equals 3 seconds. If we really should specify that as seconds, because what if it was minutes? What if it was hours? We're here 2005 and 2011. It's pretty much implied to be a year. If you wanted to write between the year 2005 and the year 2011, go right ahead, whatever floats your boat. But questions, concerns about those two before we go on to still 5-4, but a slightly different type of question. Okay. So I think I zoomed in a little bit by accident, so let me zoom back out. So here we have that a man starts 50 miles away from his house and takes a trip in his car. He moves on a straight line and his house is somewhere on that straight line. His velocity is given in the figure. Now I'm going to draw this because I don't think that t-axis stands out very well. So that's our t-axis. Anywhere that the velocity is positive, so essentially between t equals 0 and t equals 2, he's going to be traveling towards home. And then whenever the velocity is negative, it's going to represent him traveling away from home. So essentially he starts 50 miles away. This essentially tells us that he travels towards home for 2 hours and then essentially turns around and starts heading away from home again. He was on a trip far away and he started traveling home and realized he forgot his kids at the vacation house. That's hopefully not what happened. Anyway, so we want to ask, when is the man closest to home? Approximately how far away is he then? So essentially, remember let me just, because I'm going to want to scroll down a little bit. So let me write this here. So he starts 50 miles away. So when is he closest to home? Well, that would be essentially before he turns back around. Like he's going to travel towards his house and eventually turn back around. So he's going to be the closest to his house before he turns around. So he turns around at t equals 2. And that's because that's when it shifts from positive velocity to negative velocity. So he turns around at t equals 2. So he's probably going to be closest when t equals 2. So now we need to figure out how far away he was at that point. So he starts 50 miles away. So we essentially need to know how far he traveled in those 2 hours. Well, since we're given a velocity curve, if we were able to find the integral from 0 to 2, was this given a name? I'm going to call it v of t. I don't think it was given a name. If we're able to find this integral from 0 to 2, we'd be able to figure out how far he traveled towards his house. So here we're not given an actual function, so we can't do it with, our antiderivatives or our calculator even. This is when we have to go back to that idea. We're going to count boxes here. So technically you could find a right-hand side and a left-hand side Riemann sum and average the both of them. But let's do the little counting boxes method that we talked about back in 5.2, I believe. This area here looks to be approximately 1 box worth of stuff, because kind of that first one is almost half a box and the second one is almost half a box. So there's approximately 1 box worth of stuff, underneath of that function between 0 and 2. But then remember, when we're doing this counting box method, you can't just count the boxes. So that integral is not equal to 1 because we need to take into consideration how large each box is. So these boxes, if we look at kind of the units on the axes, we have that they're 1 by 30 boxes. So we have to multiply this by 30, essentially 30 times 1, and that's going to be the area per box. So, well, 1 times 30 times 1 is 30. So that's telling us that he essentially traveled 30 miles in that 2 hours. And the miles essentially comes from, well, the v of t is given in miles per hour, and the t is given in hours. So the units of the integral are in miles. Maybe I should put mi, because m by itself is usually meters. So he traveled 30 miles in that in that time frame. So our answer is still not 30. So we want to know how far away he is from his house. So if he starts 50 miles away and then travels 30 miles towards his house, he's 50 minus 30, 20 miles. So he's 20 miles away from his house. Away from his house. So we not only had to find how far he actually traveled in that time, but we had to take into consideration essentially where he was to start with, and then factor in how far he traveled. Questions on that before we go to, there's another similar type question below. Okay. So let me try to keep as much in here as possible. So let me try to zoom out a little bit. So now we want to know, when is the man farthest from his house and how far away from his house is he then? So there's kind of two options here. If you're thinking about it super generically, maybe he started the farthest away from his house. So we're kind of going to keep that 50 in our back pockets and try to compare it to a possible other answer. But if we look at this, so essentially he traveled towards home for the first 2 hours, but then he turns around and he starts traveling away from home. And he's traveling away from home in the entire time frame from t equals 2 to t equals 5. So he's also possibly farther away after traveling those entire, what was that, 3 hours? So it's possible that he's farthest away when t equals 5. So let's go ahead and look at where he is when t equals 5. It's going to turn out to actually be the answer, but I do want to remind us that technically in terms of questions like this, it could also be the starting point. But let's see where he's at t equals 5. So we already know where he's at t equals 2. So remember, at t equals 2, he's at 20 miles from home. So what we can do is, instead of having to find the entire integral from 0 to 5, let's just look at the integral from 2 to 5. And then just use the fact that he was 20 miles away from home and go from there. So if we want to figure out how much he traveled between 2 and 5, we're going to count those boxes again. So we essentially have one full box right here. And then if we kind of add, these two boxes right here, we're going to get a second box. And then between these two right here, that's approximately another third box. But then we have this box up here we haven't factored in yet. So this looks to be approximately 3.5 boxes. Everyone okay with that? And also remember, when we're counting the boxes, we're trying to get just a decent estimate. We're trying not to make it perfect because that's kind of impossible. But it looks like there's approximately 3.5 boxes underneath of that. But remember, we have to multiply that by the area of each box, which we found before was 30. So then the actual area underneath of that function between 2 and 5 is 105, and our units for our integrals are in miles. So again, that doesn't mean that he's 105 miles away from his house. That means that he traveled 105 miles. So at t equals 2, he started 20 miles away from his house. And in this next 3 hours, he travels another 105 miles away from his house. So this time we're going to add those two numbers together, because he started 20 miles away and then goes another 105 miles away. So he ends up 125 miles away. Now again, in our back pocket, we had that he started 50 miles away from his house, but 125 miles is farther away than 50, so he is farthest away at t equals 5, and he's 125 miles away from his house. Questions? Concerns? So zoom in up here. So remember, when we're using that counting box method, we need to not only count the number of boxes, but figure out the area of each box. Because if each box has an area of 30, then technically 2 boxes would be 60, 3 boxes would be 90, and so on and so forth. So that 30 essentially comes from the fact that one of these boxes on the function grid, if you will, is a 1 by 30. So 30 times 1 is 30. So that 30 comes into play anytime I'm considering the amount of boxes I have, because if I have however many boxes, I have to multiply it by this 30 to get the actual amount of area. And since the thing that I actually these questions is the area, zoom back out. That's why I need to multiply by the 30. So notice the 30 always comes up when we were doing an integral. Remember, integrals give us area. So we were counting up the number of boxes, but then we have to multiply by the 30 to get the actual amount of area. That makes sense? Any more questions about that one? All right, so next one. The rates of growth of the populations of 2 species of plants measured in new plants per year are shown in the figure. Assume that the populations of the 2 species are equal at time equals 0. So essentially this is giving us the rate. This isn't giving us the actual population. This is giving us how many new plants come into being in that time frame. And we're essentially saying let them start at equal values to begin with. So we don't really need to worry about the starting values. We can just kind of compare the amount that they've grown by. So which population is, oh my goodness, which population is larger in year 1 and then after 2 years? So first thing, I always get thrown off by this graph every time I look at it. So 1 ends there and 2 ends here. Your final exam is cumulative. It will include this information, but it will also include all the other stuff. So it is cumulative, yes. So their rates are equal at 1, Kayla. But if we want to know the actual amount that they've grown by, we want to look at the area underneath of these. So if we want to know how many new plants there were, that's going to be the area underneath of these functions. So we kind of want to compare the area under those 2 functions. So if I can try to do this, let me do like a green. So underneath of species 2, which is the lower one on the first piece, we have, the area is this much in here. And then for species 1, we have that the area is, I know that's overlapping a little bit and get a little Barney down there, but is that purple area. So essentially, if we want to know which population is larger, if they started with the same amount of plants and the amount of plants they grow by is the amount of area underneath, then we essentially need to say, okay, well, which one has more area? Well, the purple area is larger than the green area. So that means that the one with the purple area, which was species 1, is going to have more plants after the first year, because since that area is larger, that means that there's more plants. We could actually figure out the number, but we don't even have to in this piece. We just need to compare which area is larger. So for year 1, species 1 wins. Because again, since these graphs are of the rate at which the population is growing, the amount of growth is the area. Now, if we want to consider after I should be careful, for the entire 2 years. For the entire 2 years, we want to consider now the area between 0 and 2 for these 2 functions. I'm not going to try to draw that out. I think it's going to get a little too tedious on here. But if we consider that species 1, well, let me draw it in pieces. So species 1 has this area here. So it has that little like almost a quarter of a circle. And then species 2 had the little bit here, but then it started a bit faster in that second year. So we have this area. So if you think about those two and we compare their sizes, it definitely looks like species 2 is going to win now because it started growing a lot faster and we pick up a lot more area in that second half than we missed out in the first, if that makes any sense. So essentially this area that we missed out on for species 2 in the first one is less than the area that we're gaining for species 2 in the second piece. So the area underneath of species 2 is definitely going to be larger than the area underneath of species 1. So species 2 wins for year 2. So we just needed to compare the areas. Again, we could have counted all the boxes and found the actual area. And we actually are going to do that for one of the species in a second. But that sounds tedious for doing it multiple times. So yeah, so I agree that these two graphs are equal. But this graph, the graphs are the rate of population growth. So it's not saying that, what is that value? It goes over to 1500. That's not saying that both populations are 1500. That's saying that at that time, they're both growing at a rate of 1500 new plants per year. So if we actually want to know the amount of plants, not the growth rate, the amount of plants, so we essentially are looking at the integral from 0 to 1 of, let me call them S of t dt's, because that would be essentially plants per year times year, which would give us plants. So if we want to know the actual amount of plants there are, we actually want to look at the integrals. And since integrals give us area, we want to compare the area underneath of those two functions, not the actual value of the graph at that. So since the area underneath of species 1, which is the one I just shaded, is larger than, let me erase that, the area underneath of species 2. That's why species 1 wins, because technically there's a larger amount of plants in that time. I agree that that the rate is equal at time 1, but that doesn't mean that there's the same amount of plants. Does that make sense? It's weird so sorry, my brain broke. The question is asking us about actual population. But what the graph gives us, well, I should be careful with my wording. The blue lines that are graphed are a rate. So I don't want to look at the value of this. I want to look at the area underneath of the blue lines. Because if I take an integral value, that's what actually tells me about, whoa, the actual amount of plants. So we do want to look at population, but to look at population, since we're given a rate, to look at the actual population, we need to look at the area underneath instead of actual what the value of the blue lines are. Does that make any more sense? So it's just keeping track of what type of function you're given. And since we're given a rate, but we want to know about the actual population, we can't just look at the value of the graph. We need to look at something different. And in this case, it would be the area underneath. So say we want to know how much does the population of species 1 increase during the first 2 years. So again, since these blue lines that are graphed give us the rate at which it's changing, then the area underneath of that function is going to give us the amount that it changed. So maybe let me say this really quick. So say, I named this S of t, and I wanted to go from 0 to 1, and I wanted to interpret this in our cookie cutter way. This would be a change in population of plants between, let's just say t equals 0 and t equals 1 years. So essentially, the integral is telling us a change in population. So if we want to know the amount that a population has increased by, we want to look at the integral value, not the blue line value. So the blue lines are the rate, but we don't care about the rate, we care about the actual amount of plants. So we need to know the integral values. So if we want to know how much it changes in the first 2 years for species 1, so we're just looking at this this line here. And if we want to know the change in population, we want to know, oh, and we're only going to 2, so let me stop there. We're only going to year 2. So we want to know the change in population, so we essentially need to know the area underneath of that part of the function. So let's go ahead and count boxes again. I know the counting boxes can get a little tedious, and there's a lot of boxes in this one. But I'll zoom in a little bit, and let's just do our best. So let's get approximately full boxes first. So I've got approximately, I know it's not quite one full box there, but let's go ahead and just, for our sanity, let's say that's one box. A second one, a third one, a fourth one, a fifth one, a sixth one, a seventh one, 8, 9, 10, 11. Let's go ahead and call that a 12th one, 13. And now I got to start piecing them together. So these two look like approximately 1 if I group them together, so that would give me a 14th box. And then here, if I group these two together, that looks like approximately 1 more box, so that would be a 15th box. And then we've got this piece here and this piece here, which are the only things I haven't counted yet. So that one at the bottom looks approximately like 1/2 of a box. And this one at the top is so close to being 1 box. So let's just go ahead and say, for the sake of our sanity, this one will give us a 16th, and let's say that this piece brings us up to 16.5. Is everyone okay with that? There's also like a little smidgen in here, so whoop. Everyone okay with how I got 16.5? Okay. So there's approximately 16.5 boxes, but once again, we can't just count the boxes, so the answer is not 16.5, because we need to take into consideration the area of each box. Let me come up here and look at this one. Now notice that in the t-axis, I have 1, 2, 3, 4 lines that get me up to 0, get me up to 1. So essentially 1 line would be 0.25, 1/4. And then I have 2 lines that get me from 1500 to 3000. Now that would technically be 1500, but if we're splitting it up into 2 pieces, if each line is going to get me there, then that line is going to get me 750. Does that make any sense? So since from 1500 to 3000, it's 2 lines. So from 15,000 to 3,000, it's 1,500, but we have to jump 2 lines. So each line is going to be 750. And then on the t-axis, we have 4 lines between 0 and 1, so each line must be 0.25. Does that make sense? So now I gotta zoom out. Zoom. Oh my goodness. Zoom, please. Thank you. So if I want to know essentially the change in population, that's asking me for the integral from 0 to 2 of, I named that function s of t. And we found that that was approximately 16.5 boxes. And the area of each box is going to be whatever 0.25 times 750 is. And that's going to give us the area of each box. So we have 16.5 times 0.25 times 750, which gives us 3,093.75 plants. So why don't we go ahead and say about, 3,094 plants. So that means that so in that first 2 years, there are now 3,094 more plants than there were before. Now, technically, that doesn't mean that well, it could be. Technically, that's only telling us how much the population has grown by. So we might not even know the full population unless we're told the amount that the population started at. Now, we didn't need to worry about that for the first question because, again, in the original statement of the problem, it said assume that the populations of the two species were equal at time equals 0. So we don't know if they started at 0, if they started at 1,000,000. We don't know where they started. But for these questions, we don't care where they start because we're just worried about how much they've grown. So for this second question, it was asking how much it's grown, and so we've grown by 3,094 plants. There are 3,094 plants, more plants than there were at the start. Questions, concerns? Okay. That's technically 5-4. I know we're starting to get towards the end. I want to write down some of the notes for 5-5, just to make sure that I don't want to have to run into the Monday after Thanksgiving. I want to leave that for a review day. So I want to try to get through just some notes. We'll leave the examples of 5-5 to Monday, this coming Monday. And then, because yeah, wait, hold on, let me look at. Oh, I have more than I think I do. Right, I forgot about that. Right, well, meh. Yeah, let's just write this down, and we might do that first example. I was looking at the wrong set of notes and I thought it went faster than it did. So yeah, let's go just the tiniest bit into 5-5. So let me just like put 5-5 up here so you kind of know where it jumps to in case you want to make note of that in your notes. So we'll get a little bit into this, finish this on Monday, and then the Monday after Thanksgiving will hopefully be just a full review day. Again, especially since your final is cumulative, I want that time to be able to go over whatever you guys want to go over. So if f of t is a rate of change for a quantity, then the integral from a to b of f dt is a total change in quantity between t equals a and t equals b, which is why I can use that cookie cutter language of change in something between a and b. So this also means, essentially because of this piece back here, that we can solve for either f of b or f of a, the antiderivative value. And this is especially used when the integral is too complicated to solve by hand or just gross to solve by hand. So essentially the way that that's going to happen is if we have this statement, which is essentially the fundamental theorem of calculus. Say we wanted to solve for f of b. Say we wanted to get f of b by itself. We could do that by just adding f of a over to the other side. And now we've got f of b. Now, if we want to solve for f of a, it doesn't get much more complicated. It's just that the algebra has one more step. So if we wanted to solve for f of a instead, what I would do, there's a couple different algebraic ways you could do it. But what I would do is I would still add f of a over to the other side. But then if I want to get f of a by itself. So the reason I still add it over is because if I subtract the f of b, then I still have a negative in the front, and then I have to divide everything by a negative, and that gets gross. So essentially we can solve for f of a by just then subtracting the integral over to the other side. Now for these, technically, you could memorize their forms. I just remember this and do the algebra when I want to get one of them over the other. But technically, you could memorize them if you wanted to, but I think it's just not worth memorizing if you can get there algebraically. So, let's see, 3 minutes? Yeah, we can do this first one. I might review it a little bit on Monday, but we'll talk about it. So say we have a bacteria colony and initially has a population of 14 million bacteria. Suppose that oh my goodness, I can't read. Suppose that T hours later, the population is growing at a rate of 2 to the T million bacteria per hour. Give a definite integral that represents the total change in the bacteria population during the time T equals 0 to T equals 2. So total change, well, that's what our integral represents. So we're going to have the integral from 0 to 2 of 2 to the T dt, and that's literally all that question wanted. So we just wanted the integral that's representing the total amount of change. So that's going to be the integral of the rate, which we're given. We're given the rate. So say we wanted to find the population at time t equals 2. Now technically the population, let me try to keep a little bit of this in. So what we want is we want big F of 2. So we essentially want the antiderivative at 2. Now, in terms of anything you'd see on an exam, it would have to be able to be done by hand. For those of you who don't have a calculator, well, actually, I'll talk about that later. Because your final exam's online, I can probably give you all an online calculator you can use. Anyway, so we want that. So if we think about what the integral technically gives us, this would be f of 2 minus f of 0. So this is what we want. No, it won't be on lockdown. So if we want f of 2, let's go ahead and get that by itself. So what we would need is we would need to add f of 0 over to the other side. Now, while you might not think so, we know both of those values on the left or can find them. Since we're running short on time, I'll come back to this. We'll talk about it a little bit more on Monday. But on the left, that integral, you can just punch into your calculator if you have one that can do so. And if you don't, for the final exam, I'll show you a online calculator that I actually don't hate, because it doesn't do things that it shouldn't do. Anyway, I'll talk about that more when we get towards the final. So here, if we plug that integral into our calculator, we get 737.22. Now, technically, we'd also need f of 0. Now, that would be the starting population. In the original question, we're given the starting value. So f of 0 is 14. So now we've found what we wanted when we just add those two numbers together. 751.22. We're out of time. I'm going to talk about this one again on Monday. If you have any questions, feel free to stick around. Otherwise, have a great weekend. We'll pick this up on Monday and finish this on Monday. And then we're pretty much done. Just got a final to do. So. Yeah, no homework this weekend. You can thank your test for that.